Hello team, this is Kevin Leach with CS3276 with a video about getting started with Programming Assignment 1 in this class. Now, I've at this point already made two other videos about setting up an appropriate environment with the reference compiler in Windows, using both standard Windows command line as well as the Windows subsystem for Linux. In this video, we're going to kind of take more of a focused look at getting started with writing software, writing a program in Python. Again, depending on your backgrounds, maybe you're not as familiar with Python, maybe you took a course in Java or C++ before, so I wanted to have kind of a level playing field. Now officially, this is an upper level elective. You should at this point have a willingness to pick up new programming languages. Python in particular is once you get used to the eccentricities like the requirements about white space, Python is actually an extremely powerful and widely used language these days. And so I believe that you will be better prepared for being competitive in the job market if you also know or are familiar with Python. And so that's one of the intended goals or kind of outcomes of this course. So all of the programming assignments will be done in Python, and so that's this is the PA1 is intended to be kind of a nice way of a structured way to getting started with that, to make sure that you have enough familiarity. Now, in PA1, there are two parts to it. The first part is a Python implementation, and then the second part is a cool implementation. So PA1C, that's due a week later. PA1C has you do the same type of the same algorithm in cool. Now in this class, again, we are making a compiler for cool programs, and so we want you to also be familiar with writing software in cool so that you can use that skill to essentially make test cases for all of your subsequent submissions in this class. So all of the code that you'll turn in is going to be written in Python. It would be beneficial to you if you also know a little bit about how to write cool software so that you can make good test cases for all of the things that you turn in. So this assignments, you will be writing a topological sort or topo sort implementation in both Python and cool. For this video, we will focus on how to get started in Python. We'll have a separate video on getting started with cool. Loosely, topo sort is a graph algorithm that produces, it takes a graph as input, so a set of vertices and edges, and also possibly weights, although that won't be relevant for this assignment. Takes that graph as input, and it produces a list of vertices as outputs, and that list is ordered according to the parent and child relationships between nodes. Essentially, the first node in your output list are the nodes that don't have any incoming edges, and then the last node, the last vertex in your list are the nodes that don't have any outgoing edges. And so the topological sort, it kind of captures the parental relationships. A node cannot appear in the output list until all of its parents have appeared first. So that is the goal of topo sort. It will come in handy later on for PA4 when we're doing type checking. It turns out you could do topo sort on your program's type hierarchy and detect cyclical inheritance, which is a problem that you'd want to output as an error potentially. So that'll come in handy later for PA4, which is why we're doing it here. We're not going to exactly cover topo sort because that is the goal of the assignment. That is what you were supposed to be doing. And instead we will cover something that might be relevant or potentially useful in completing that implementation. We'll be looking at Dijkstra's algorithm today in Python. Dijkstra's algorithm, you may have seen it before. It is a graph algorithm that tells you the shortest path within a graph between some start node and some end node. And so it's a very, very important algorithm in, among other things like network routing. And so we'll be doing that implementation today in Python, just so you can kind of get your bearings with writing software in Python and how it might work. So with that, let me convince OBS to work and go to the window plus face view. All right, here we go. I'll just mention briefly, so like I said, the two other videos that I've already done show you how to get started with Windows environments. I don't own a Mac, but it is also possible to complete this class with a Mac. That you should be totally fine. There is a version of the reference compiler for Mac, if you so choose. However, regardless of what your preference is, my recommendation is to use Linux, and specifically Ubuntu 20, if possible, for a couple reasons. First, from the mercenary, class completion perspective, the autograder in this course that we are using to evaluate all of your submissions is running Ubuntu 20 under the hood. And so if you want to match that environment as best as possible, maybe you'll want to use Ubuntu 20 locally. The second part, though, is perhaps more importantly, I am thoroughly convinced that felicity with Linux and the Linux command line will make you more competitive on the job market. I cannot think of a single company that does not expect, or at least touch on a little bit of Linux command line usage, whether it be to remotely access servers with SSH, or to run complex system software. Having a little bit of familiarity with Linux is extremely valuable, and so I recommend it highly. Again, both for this class, but also just as a way of making yourself more competitive as a software developer by the time you graduate. So with that said, I have this environment set up. I'm running a Windows machine, but I have a virtual machine set up that's running Ubuntu 20.04 under the on it. And you can do that too if you want help setting up a virtual machine. We can do that during office hours. That is our recommendation. Whatever the case is, however you're following along, if we're going to get started with PA1, the first thing you'll probably want to do is to consult the course website on which we will find, among other things, a specification for PA1 conveniently listed. There's a bunch of stuff that you should probably read for completing the assignment itself, including some example inputs and discussion of what is valid, and what your input assumptions are for the assignments proper. For today, again, we are going to do a Dijkstra's algorithm implementation in Python. If perhaps I don't know where to begin, I might look at these convenient resources, and there seems to be this hint zip that might have some useful, cool stuff in it. Maybe I will bring up a terminal here and go to the downloads folder, and I appear to have already downloaded it, no problem. I've already unzipped it as well, so let me just go into this. Well, for good measure, I will make sure to show all of the steps here. I've downloaded this PA1 hint.zip file from the internet. I will unzip it here. By the way, tab completion works in the terminal, so I can just do that and save some keystrokes. In this directory, I see a bunch of cool files here. I guess one cool file and a bunch of other mediocre files. But there's a README that perhaps you should look at. And then there's a bunch of implementations of this thing called unsort. Now, again, it's discussed in the README already, but what these programs do, they all do the same thing. They will take in input from standard input, and they will sort them in reverse alphabetical order, and then print them back out to the screen. And so, again, before we look at any source code here, suppose that I look at this example.list file. It has a bunch of strings in some random order. If I were to run this through the Python script here and feed that as to standard input, well, look what happens. It reorders all of these strings in reverse alphabetical order. Wonderful. And so, again, just we have the same program just implemented in several languages, if you want to kind of compare and contrast, or depending on what you're already familiar with. Regardless, we're going to be looking at Python, and so why don't we just open that file up and see what's going on. just first kind of quick overview. At a high level, what we're doing is we're getting all of the lines from standard input. We are doing something to remove some white space. We'll come back to that in a second. And then we are sorting it in alphabetical order by default in Python, and then reversing them. And then we're going through one line at a time and printing them back out to the screen. And again, if maybe you're not super familiar with Python, but you can kind of reason from first principles and see how that kind of plays in. You seem to be reading a bunch of lines from something called standard inputs. There's some function here that does something cool, and then we're just sorting and reversing and doing like a for loop, right? So hopefully these, again, if you've never seen Python before, hopefully these are kind of familiar keywords or structures that you've seen in other languages regardless. Now, a more thorough look, again, if you're not familiar, what Python has is this import keyword. That is its way of bringing in or including code, functions, methods, data structures from already existing libraries. In this case, we're importing from something called sys. Sys just includes a bunch of like operating systems things that might be useful. For example, it gives you access to standard input fairly directly, and so we can treat this as a file from which we're reading a bunch of lines. So the readlines method will return a list, which is a built-in type in Python, of strings. Right? So we'll read in all of the lines from standard input, throw them into a list. Great, everyone's happy. Now, there's also an ability to define functions, and again, Python is an imperative language that also has some object-oriented features. That means it's reading code from top to bottom and executing it, so you can define a function here and then call it somewhere else in this program, no problem. What this helper function is doing, it's called strip list. What it seems to be doing is producing some magic list in some formats that perhaps you've not seen before. This is something called a list comprehension in Python. What this does is this syntax produces a new list where you get to specify what each element is by applying operations or transformations to elements from some other input list. So what's happening is I am going through every element X in my list, that's the input to the function. I go through every element in that input list, and then I apply this rstrip method to each element. Rstrip in Python, again, no need for you to have memorized this, but what rstrip is doing is it's removing white space from the end of a string. So remember, I'm taking all of these strings from standard inputs. I have a list of them. Well, what I want to do then is remove all of the extra white space from the end. This can be a potential issue because, again, if I'm taking lines off of standard input, well, what it really looks like is if I have a whole line, that's going to include the new line character at the end, and so there is a difference between if I type in X versus X with a \n with a new line character, and so I'm going to remove having to think about that by just doing rstrip on every line that I get out of standard input. So that's the purpose of this helper function. So I do that. Strip list returns a new list, so I get a copy of all of the strings with white space removed from the ends of each string that I just got. Then, I just have a list. I will do dot sort. In Python, dot sort is what's called a destructive in-place sort. It doesn't produce a new list. I'm just rewriting all of the elements in the existing list. Similarly, reverse does the same thing. It's the same type of function. It is a destructive in-place operation where I replace all of the elements in that list. And so I am sorting the elements and then reversing them. And then again, conveniently in Python, we have this type of iterator format where I say, for every element, so for one line in my list of stripped lines, I just print them out one by one. Okay? That's what's going on in this Python script. Our goal, though, is to do something a little bit more than this. I want to make a Dijkstra's algorithm using Python. So how is that going to work, and how can I use pieces here in this starter hint code to make some progress? So what I'm going to do is I will make a directory CS3276, come in here, and I'll make something maybe for PA1. Sounds great. And then I will, have some sort of PA1.py script that I'll work on. Now, maybe I don't know how to get started here, so I'm going to bring back up the starter hint code that I just had. So it's unsortpy.py, maybe I'll refer to this as I'm trying to make this Dijkstra's algorithm implementation. All right. So what do I need? Remember, Dijkstra's algorithm. And by the way, for good measure, you should probably just include your name and your VUNet ID somewhere, or better yet, your Vanderbilt email address somewhere at the top. That's a good practice. You should probably be doing that. All right. So I want to do Dijkstra's algorithm. What does that do? Take a graph as inputs. Report shortest path between some source node and some destination node. That's my high-level goal. I want to be able to give this a graph, and I want to report for some source and destination node what's the shortest path between them. Well, what is that going to require? Well, it sounds like I need some representation of a graph. Maybe I don't remember how that works. I could consult the Google, and maybe I'll just look for something on Dijkstra's algorithm. Maybe we'll come back to the Wikipedia article. Jimmy Wales probably has something useful to say. But maybe I just want to get started by looking at some type of example graph to remind myself what the input might look like. And, all of these look pretty good. I think what we'll probably start with is we kind of like this one just because it also has this nice table off to the side where we can kind of check our intuition later on. And so we have this graph. There's 5 vertices labeled A through E, and then there's some edges between them. The edges are annotated with weights, and our goal with Dijkstra is to say, well, if I want to go from node A to node C, what's the path I should take according to with the goal of minimizing the weights between the edges along that path. All right. So I need a way of capturing this in my program if I'm going to, deal with this graph and then find some shortest path through it. So how's that going to work? Well, I could think of this graph as a collection of edges. Maybe I have some sort of edge list where I say, well, I'll have a list of tuples where every tuple contains the start node, the weight along the edge, and the end node. And so I could say, for example, well, this graph consists of some elements where I start at A, it takes weight 1, and it goes to D. I start at A, it takes weight 6, and it goes to B. I just have a big list of that and capture all the edges in the graph. So I could totally do that and then have that as an input that gets fed into my program. So how might I do that? Well, I need some type of input handling. So first thing is read in a graph from standard inputs. Maybe I'll have a format where I say the input goes some start node, some weight, and then some end node. And so I'll have these chunks of 3 lines at a time that come in through standard input, and that's going to capture my graph representation that I can process and deal with. So I'll just read in a bunch of those 3 lines at a time and do some stuff with it. All right, so that's kind of part 1, read in the graph from standard input. Well, next, after I do all of that reading, I need to put it somewhere in some type of data structure. So I need to have organize the data into some type of data structure, into some data structure, so some graph structure that will be useful for processing later on. Maybe an edge list. Who knows? And then part 3, I guess more detail needed, but we will actually do Dijkstra's algorithm where we're going to produce some type of shortest path between a specified start and end node. We'll come back to that one later after we deal with these first two things. So that's kind of our high-level plan. Let's get started. So I said I want to read in a graph structure from standard inputs. Sounds like I need to read things from standard input. Maybe I could just borrow the lines here and get started. So I want to import sys and then create some type of list structure that contains all of the lines from standard input. Sounds great. One thing that I'll want to do, and I encourage this in general, is to test early and often. And so I want to make sure at this point that I didn't screw anything up when I copied and pasted the code. And so maybe I want to make sure that this works so far, and I can get back all of the, I can sort of echo back all of the lines from standard input. Sounds great. What should I do? Well, for every line in lines, why don't I just print out the line and see what happens. Now, I already have this, or I had before this example.list thing that I don't have anymore. And so maybe I'll just have some sort of simple graph input that might come in handy later. And let's just say I'm going to create the world's simplest graph. I'm going to have one edge between two vertices with weight 1. So I'm going to have a graph where I start at node A, I have weight 1, and it goes to node B. Sounds like a plan. Maybe we could start with that. And again, this is just 3 lines of text so far. Let me just make sure that my script can read that in and then print it back out to me. So I'm going to say Python3 PA1.py, and I'm going to give it this simple.graph thing as input. And look, wonderful, it kind of echoes things back. But notice, by the way, I seem to have a bunch of extra white space that came along for the ride here. And this gets at what we saw earlier with this helper function. When I'm reading in from standard inputs, each line here that's returned by readlines has the extra new line character in it. And so the print function also inserts a new line, and so now I have 2 new lines between each line. Maybe I don't want that. Maybe that extra new line thing is confusing. And so why don't I just say, I'll borrow this list comprehension that we saw earlier in this starter code, and I'll say, I'll just overwrite lines with a version of lines where all of the white space is removed from the end of each string. So I'm going to overwrite lines with a new list where every element gets rstrip applied to it. Now let's see what happens. If I run the same code again, great, the extra white space is gone. This is exactly what I want. All right. Remove, and so we'll just document our code as well. So we're going to remove extra white space from the ends of each line read from standard input. To keep it readable at this font size, I will do it that way. All right, great. So, wonderful. I'm able to read things in and print that out line by line. So I kind of have part 1 here sort of done. So I'm reading things in from standard input, but I want to make sure that I'm reading 3 lines at a time. Remember, our high-level plan was to read in a graph, and we are representing the graph by saying the first line is the start node, the second line is the weight, and then the third line is going to be the destination, the destination node, and so that way I can capture edges within my graph, and I'll just have a file with lots of those edges listed out, and so I need to read in lines 3 at a time. So how's that going to look? Well, I have a list of lines already. Maybe I want to construct a for loop that goes 3 lines at a time. How could we do that? Python has this nice syntax where it you can use this helper function called range, where it will allow you to iterate over a list of numbers according to some criteria. And so I want to do a for loop that goes from 0 to however many lines I just read in from standard input, and I want to go 3 lines at a time. Right? So I have this nice format for reading in, or sort of going 3 at a time in this for loop. How am I going to use this? Well, I will have a source node, which is going to be the first line in a group of 3 lines. I'll have the weight, which is going to be, starting at I. I'll have the weight, which is the next line in the group of 3 lines. And then I'm going to have the destination node, which is going to be the third line, so I plus 2 in a group of lines. So I'm reading 3 lines at a time, and I'm treating each line according to this format that we specified earlier, source, weight, destination. Right? So I'm just going to do that 3 at a time and read in the whole graph. All right, so maybe I could test this so far before going any further. Well, I'll just make a nice print statement out of this. By the way, Python has nice support for doing formatted printing, where I could say something like the source node, and then the syntax means that I will replace it with something later, with a variable name. Source node S goes to destination node D with weight W. And in Python, the way that you deal with this is you can apply the .format method, where you can provide the syntax completion's getting in the way, where you can provide a list of all of the things that need to go into your string, right? So these curly braces let you specify tokens that can be replaced with something that's relevant, right? So like format strings in C, or like in Java, you can print out variables and so forth. This is how Python does it. So I can say, well, for each of these symbols that I just created in the format string, I need to provide data for them to make Python happy. So I'm going to say S is whatever I just pulled out as the source node. I'm going to say D is, the order doesn't matter at this point, by the way, so we'll just say W is whatever the weight is that I just got out of the standard input, and then the D is the destination node that I just got out, right? And so I can apply that as a format string and then print that right out. And so now what I hope is for every edge that I read from standard inputs, I will get to see this string that tells me about what each edge is doing. Right? Let's see if Python will be happy about this. Cool. So if I provided that this simple.graph as inputs, again, there's only one edge defined there, and I have one edge that goes from source node A to destination node B with weight of 1. Maybe at this point, maybe I want to have a slightly more complicated test case, and so I'll just do simple2.graph, and I'll have the same edge that I had before, A goes to B with weight 1, but now I'll also have a second edge where I have A goes to C with weight 2. So now I have 2 batches of 3 lines. Each of these 3 lines defines a separate edge. Right? So now let's see what happens if my program takes that as inputs. Great, now I have 2 edges reported. A goes to B with weight 1, and A goes to C with weight 2. Sounds great. So I've kind of done this first part now, so done. Before moving on, again, I want to make sure that I am documenting things properly based on what I've just done. So I want to read in lines 3 at a time. In each group of 3 lines, line 1 is the source node. Line 2 is the weight. Line 3 is the destination node. Right? So that's what I'm doing here, 3 at a time. All right. So I've kind of finished this first part. Now what I need to do is kind of part two here, which is to put it in some type of data structure. We suggested earlier, maybe we'll use an edge list. Basically, I'm going to say that my graph is going to be represented as a list of tuples, or I'll have some source node, weight, destination node. In an incredible surprise move, this matches the input format that we specified earlier. Maybe that's just convenient, so we should go with it. So we're going to just have a big old list of these 3 tuples where I capture each of the edges in the graph, and that'll be enough to represent the whole graph. Now, there are other ways to represent lists. Some people will do like an adjacency matrix, and will have some complicated map structure where they map each vertex to the list of children nodes and so forth. There's different trade-offs that are involved in each. This edge list thing is a more straightforward implementation, but it's also potentially not as efficient in theory, because you have to traverse the list every time you want to find out something about a particular node in the graph, for instance. Other representations can be faster. But for sparse graphs, or for the purposes of this assignment, an edge list will do just fine. So how are we going to do that? Well, it turns out Python has a built-in list, and it also has a built-in tuple type that will make this pretty straightforward. So before this for loop, I'm going to create a variable. So like make an edge list that we can use to analyze the graph. So I'm just going to make an edge list. I'm going to say it's an empty list, right? These square brackets means you get an empty list, and I'm going to add elements to it. And so now, rather than printing everything out, which, maybe is kind of cool, I'm going to instead add the information that I just got. So remember, I'm reading in edges by reading lines 3 at a time here. I'm going to append a tuple, which I express with these nested parentheses here. I'm going to make a 3 tuple where I have the source node, the weight, and the destination node, and I just put that into my list. All right. Again, before moving on, let's make sure that it's working. So appends new edge to edge list. What I'll do to test this is I'll just go through for every edge in the edge list. Let me just print out what that edge looks like and see what happens. Wonderful. So I have my 2 edges that I have in this simple 2 dot graph. I have A goes to B with weight 1, A goes to C with weight 2. Now at this point, things are pretty good, but if you notice, these single quotes represent a string literal in Python. And this is fine for the nodes, right? They're going to be named something like a letter. But for the weight, that might be a problem. We don't want the weight to be a string. This is a number that we're going to have to, compare and use math on later if we're going to be using Dijkstra's algorithm. So we probably want to turn that into an integer type rather than a string literal. Well, again, pretty simple to do in Python. All you need to use is the int constructor to coerce the string to become an integer, and now Python will convert it for us into a string. See, the single quotes are gone. That means that this is an integer type, so we can do normal math with it rather than treating it as a string. Sounds great. So now we've, at this point, I don't think we need this hint code anymore. It's not going to really help us at this point. We'll close that out. But we have successfully read in all of the edges from standard input. Now, the next thing is, we've kind of finished this part, so done. Now we need to do this mysterious step with where all the work is, which is to implement Dijkstra. So how's that going to work? Well, I don't remember it off the top of my head. I am sure all of the students surely have it memorized, right? But I don't. I am not cool enough. So we will look at the Google again and bring up this Wikipedia article and perhaps Well, maybe you should read the wall of text, who knows? But there seems to be some conveniently placed pseudocode that isn't quite Python, but maybe I could think a little bit and turn this into Python. Incidentally, we want you to write the code, right? So please don't Google and copy and paste someone else's Python code. Please think through the algorithm to make sure that you're understanding how to actually do it in Python. In any event, we could start here in this. We could borrow this almost Python code kind of piece at a time. And just to kind of look at it real quick, what it seems to be doing is it goes through every vertex in the graph. So maybe we want to collect a list of all the vertices, and it adds it to some work list. So this seems to be a work list algorithm where we build up a work list and then go through each element in that work list and then establish something about the shortest path from each node in the graph to every other node in the graph. So that's kind of what they're doing here. They're building up these two maps here. So they have a distance map, which is capturing the distance from the source node to whatever other vertex there is. So you kind of build that up for every node, so you know it for sure no matter where you are in the graph. And then they also have this previous map. This will help us build up the path. So remember, with Dijkstra's algorithm, like, yes, we want to make sure we have the smallest distance. So we want to know what the shortest path is, how short it is. But we need to also know the path itself. And so we want to keep track of, if I'm at any particular node, which other nodes do I go to form the shortest path back to the source. So that's kind of the way that I think about it. This previous dictionary is going to help us track which nodes do I need to go through to ensure I'm taking the shortest path back to the source. Right? So we're building up both of those two things, and then we're going to use a work list algorithm to get through it. Maybe I'm not so great with algorithms, and so again, I'll just start by borrowing this code and doing something with it. So I'll get rid of that debug printing. I will print or paste it here. Sure, sounds great. By the way, if you're on the Linux terminal, Control-Shift-V will do paste. That is a common beginner's trap. Students often wonder, why does Control-V not work? Well, it's because arbitrarily it needs to be Control-Shift-V for reasons unknown. Anyway, I will borrow this code. Again, it's not really Python, so I'm not going to try and copy and paste it here directly. I'm just going to look at it here for reference and try and figure something out. So the first thing, again, what I want is some way of getting all of the vertices. So we might be rescued again by list comprehensions and other cool built-in things in Python that make our lives super easy. I want to have some sort of vertices list, and so, I guess technically it's a set, because they're the vertices each vertex can only appear once. We'll come back to that. So how do I get the vertices out of my out of what I have so far? So I have an edge list structure. So I have these 3 tuples that have start and destination node in them. So I want to round up all of the source nodes from each tuple, and I also want to round up all of the destination nodes from each tuple, and then throw them into one giant list. That will help me capture all of the vertices that are in my graph. So how will I do that? Well, again, I can use list comprehensions and make this very, I guess, Pythonic or super convenient for us. So at its heart, again, I have these 3 tuples in my edge list. So I want to collect something from each of the tuples in the edge list. In particular, I care about the source node, which is the source node. So the first element of each tuple in my edge list, that's the source node. I want to get all of those. And so my list comprehension is going to say, I want a list of source nodes where I go through each 3 tuple and I pull out the first element. So for this 3 tuple in my edge list, so for every 3 tuple, I'm going to care only about the first element of each tuple in the edge list, and I'm going to make a list out of just that part. Great. So that'll get me all of the source nodes, but remember I also have all the destination nodes that I can't forget about. Those are also legitimate vertices in my graph. So conveniently, I can just add to my list another list comprehension, and I'll say, well, I want the destination node for, and this time I, by the way, you can wrap lines by ending in a backslash. So I'm going to add in this other list comprehension where I get all of the destination nodes, and this time I care about the third element of each tuple in the edge list. All right, so sounds great. Again, maybe I should test so far. So collect all the vertices by gathering source nodes and dest nodes from edge list. So maybe I want to test this so far, and I just want to check, like, well, for every vertex in vertices, what does it think we have? Let's see. All right. So I run this. It runs just fine, and I seem to get all of the vertices, but I also seem to get a bonus vertex. I have a second copy of A. This is happening because, remember, in my simple 2, I have A goes to B, and then A goes to C. So A is appearing twice. And again, what I've built up here is a list. So I need some way of making sure that I don't have duplicates because, you know, the vertex is uniquely named in our graph input here, right? So I need a set to make sure that there's no duplicates. Conveniently in Python, I can use the set constructor. And I think that will work. Let's see. Up arrow more. And great. Look, I have a nice set. So I have each element listed in, each unique element listed. So now I have a nice list of vertices in my graph that I can work with for Dijkstra's algorithm. Awesome. So, and by the way, we've already written the first part of this for loop. So for every vertex v in the list of vertices, let's do some stuff. It seems to want some distance and previous dictionary, as discussed earlier. Well, you know what? Let's just do that. So we'll have, create dist and prev maps. Or in Python, they are called dictionaries. So we will create a distance dictionary using this empty curly brace structure and an empty previous dictionary using this curly brace structure. And what I'll also do for good measure, since they want me to add to something called Q, which is presumably a set, I will just say Q is some empty sets. Amazing. All right, so for every vertex in vertices, it wants me to say the distance to V is infinity. Now, for your assignments, you'll want to do a little bit more Googling here. There might be some, like, max int constant that you could Google for. For now, we'll just say 7 nines is good enough. Close enough to infinity for the sake of this example. And the previous V gets something called undefined. Remember our the previous dictionary maps from the current node in the graph, which node should it go to next to ensure the shortest path back to the source. Back to the source node. So this previous dictionary is mapping one node, so like A, into another node, like B. And so what we're expecting is some type of node name. Again, you'll probably want to do something a little bit more sophisticated here. We'll just use a question mark. And that might be good enough to say, like, well, that's a node name that we don't use in our inputs. We'll just use that to mean that it's undefined. Now, again, in the autograder, there is probably some type of test case where all of the node names are confusing symbols just to be evil bots. So, think carefully about how you might resolve that, perhaps using some type of exception or special, class type or something. Plenty of solutions to that issue. But for now, good enough. And so I'm going to initialize these two things for each vertex, and then I'm going to add v to q. Well, there is an add method in this Python set type, so I will just add v to q. Awesome. All right, so going back to the Wikipedia page here, like what's next? So we've initialized our distance in previous dictionaries, and now we have added v to q. Oh, there's one more part here where I have to say the distance to the source is 0. So remember, there's when we're running Dijkstra, we have some starting node, and well, later on we'll also have an end node. But we have some starting source node, and so the distance between the source node and itself is 0. That is probably something we should also just add for good measure. I'll just say dist of source. In this case, we'll just say we're starting at A equals 0. All right. And so now we're saying while Q is not empty, so I don't think the Python set has like a direct is empty thing. But what we can do is say, like, well, while the length of Q is not equal to 0, well, I guess greater than 0. Let's just say not equal to 0. I can't imagine a case where it would be negative, but, whatever. That should be fine. So, while, this, by the way, this should be at the correct indentation level. So while the length of Q, so while the Q is not empty, we want to have something called U, which is a vertex in this set with the smallest distance, to it. All right, okay, great, I see. Right, so not the most intuitive pseudocode. We want to find a vertex with the smallest distance, because that will help us identify, well, which node should we go to next if we're trying to form a path back to the source. And so we're going to have to go through all of the distances that we just initialized and find the smallest one and say that the node that it belongs to, that's the one that we're going to remove from Q, and then do some other stuff to it. All right, so again, for good measure, let's just, borrow this code for a second. We'll remove this code. Too much tabs still. Get rid of that. All right, good. All right, so for we need to have some node or some vertex U with the smallest distance. Okay. What we could do is to say, so there's a few different ways of doing it. I'm tempted to say, there is a min function where we say, that may be too complicated. So there's like a min function where if you give it a list of numbers, it will produce the minimum. But the problem is we want the key of the dictionary for which the value is minimum. And so, like, we could probably do this. It might just be easier to have like a for loop. So what we're going to say is, we're going to start off with an undefined node, and I'm going to say for each key in distance.keys. So I'm going to pull out all of the node names, and I'm going to say If distance k is less than min, then I'll say u equals k, and min equals distance to k. So I need some other thing here. Minimum, again, I'll just use 7 nines and eventually find the minimum this way. Super hacky, but this should work. So I'll go through the list of the distances, and then I'm identifying the node in the graph for which the distance is minimal. And that will be it. At the end of this for loop, I have some value in place for u. Now, what it wants me to do is to remove u from Q. So, Q dot remove u. Right, just again to document. So, find the vertex u that has the smallest distance to it, using the distance dictionary. Initialize to unknown vertex. Placeholder for like infinity. And remove the found vertex from work list. Cool. So what I want to do now is some other magic here. Maybe what I can do is test it at this point to see if it even does something. So maybe I just print out for good measure, found some node u where I say, well, u equals u, whatever it was. And then I'll print that out and see what happens. All right. Uh-oh, we have a problem, a key error. Line 74 says key error on A. What does that mean? Cool. So we're trying to remove A from the list, it seems, multiple times. Why is that happening? I see. All right, so notice the pseudocode is right, and I somehow did not see this. What it's asking us is to identify a vertex u from the work list Q. And sadly, what I've decided to do is the tragic mistake of using the entire distance dictionary each time. The work list is going to shrink as we remove nodes from it. Distance is not going to. That's going to maintain all of the distances. I should not be looking at that. I should instead be making sure that I just go through all of the vectors left over in Q and then checking the distance dictionary against that. All right. So now it's complaining that it's finding node question mark. This is probably because we haven't completed the algorithm. It's basically when it iterates over this, there's no other stuff in Q left, and so there's no other node that it can find that meets this criteria. And so that is a problem. So let's implement the rest of this algorithm. So we've done this part so far, and now we want to say for each neighbor v of u that is still in Q, for every vertex for which there is an incoming edge from the u that we just picked that's still in our work list, let's do a bunch of stuff. All right, so what that means is we need to find all of the neighbors of u. All right, so we should be able to do this with a list comprehension. So I want to have neighbors to be this list. So we'll construct this using a list comprehension. So thank you, Mr. Rogers. What a wonderful day in the neighborhood, indeed. All right, so we want vertices for so for every tuple in the edge list, we want all of the edges that go from U to V in edge list if U equals U. All right, so we have to create a new binding here. So I think this will work. We will find out in a second. So for every tuple that exists in the edge list, we want all of the vertices that are destination nodes that come from node U. And there's this extra obnoxious piece where I have to say what the criteria is for the U here. That's going to be that I want whatever this is to match the node that we just removed from the work list. I believe this will work. Why don't we see what happens if I just print out neighbors at this point, assuming it will parse. All right, so great. So if I just looked at node A, that's my start node, I indeed collect my neighbors B and C. Remember, my graph was an edge goes from A to B, and another edge goes from A to C. Still have a bit of an issue. Again, we haven't finished with the rest of this part yet, but we're collecting all the neighbors. All right. So for neighbor V in neighbors, if these two things match, and we want V in Q, and again, I believe that will work. Let me do that real quick. All right, so again, because of this extra part here, they still have to be in Q. So every V still needs to be in Q. So in addition to matching the source node, we also want to make sure that it's still in Q. All right. Good, that appears to still work. All right, and now we just want to finish up with the rest of this loop here. So for every one of those neighbors, now we need something called alt, which gets the distance to U that we already have established, plus something from the edges. Oh, it wants the edge weight from U to V. So how will we do this? Let's say we could do another list comprehension where we have weight for U. So for the source, weight, and destination in edge list, if we'll do the syntax again. If U equals U and V equals V. This will give back a list. We'll just take back the first element from that list to make sure that it's a normal integer. Maybe test that so far. All right. So notice, well, I mean, you know, not that you'll memorize this for every graph that you do, but remember we had an edge from A to B with weight 1, and an edge from A to C with weight 2. It seems to be picking up those weights with the code that we just wrote. So this seems to be doing just fine. This is not the prettiest of syntax, but you know, again, you could probably do it. There are plenty of other things that you could do. For example, just like having another for loop to pick out the specific edge, or to use some other type of, there's like a filter method in Python. There's a whole bunch of different ways of doing this. This will work for now. All right, so I've computed alt, and I say if alt is less than distance to V and distance to U, let's say, is less than 7 nines, then I do this stuff here where I say, well, distance to V is whatever alt is, and remember, I need to keep track of the path eventually. What this is saying, so what this is saying now is, I have found, so I've gone through all of the nodes that I have left in my graph that need a shortest path from the source to each of those nodes. And so I establish a work list to get through all of the nodes that are in the graph. And what I do is I find, I start by looking for, it's kind of like this greedy approach where I look through all of the, if I start at the source node, I look through all of the other nodes and figure out, well, which node currently has the shortest distance in the graph. So for that node that has the smallest distance, let me look at all of the neighbors and directly compute what is the shortest path from that source node to each of the neighboring nodes. And so this, kind of percolates through the whole graph. Again, if you'll notice here, if I start at node A as my source, I remember there's this part up here where I initialized the starting node to have distance 0. The first iteration of this loop is going to pick out the source node as the first node that gets removed from the work list. And then I compute all of the neighbors from that start node, and then I identify, or I basically compute what is the smallest distance that it would take to get from that start node, A, to each of the neighbor nodes. And that it's just using the weight that exists on each of the edges there. All right? So that's kind of what's happening here. All right. In addition to the weights that I'm computing, there's also this previous dictionary. Remember, that'll help us build up the actual path itself that needs to be taken from the source to the destination. The way this works is, once I have found for each of the neighbors for which I'm computing the smallest distance, what I'm saying is, if I'm at node V, the shortest path to get to node V must have been through node U. That was part of what the computation up here was for. It was finding what the current shortest path could be through the whole graph. All right, so fairly direct. Now, that seems to be it. Let's see what happens. Now, at this point, I haven't really specified a destination node. Dijkstra's algorithm, this implementation, will compute the shortest path between the specified start node and every other node in the graph. And so what I expect to see is, if I'm printing out distance, that's going to tell me what is the computed lowest weight, sum of weights, to get from the start node to each node that's in the graph, organized according to node names. And then this previous dictionary is going to tell me, for every node in the graph, which node must I go through to form the shortest path back to the source. So we'll see that in a minute. So we're going to print out the distance dictionary, and we're going to print out the previous dictionary, and we're going to take a look at that. All right. How do I interpret this? So my dictionary here, this first one is the distance. And so what I'm saying is, intuitively, if I start at A and I want to go to A, that takes 0. I'm already there. If I want to go from A to B, it takes weight 1, which makes sense. That matches our intuition for this graph. And if I want to go from A to C, it takes weight 2. Again, that was part of our input. There was a single edge from A to C with weight 2. There's no shorter way to get there. Similarly, for my previous list, it's going to tell me how to get to a node, how to get back to the source node from each node in the graph. For node A, I'm already there. There's nothing that I go through that comes before it. I'm kind of hosed. But if I start at node B, or if I want to get to node B, I have to go through A. If I want to get to C, I have to go through A as well. Seems working for this small graph. Let's see if I can make something more complicated. Before that, I want to make sure that we're documenting things appropriately so that everyone is on the same page here. First, Q. This is a work list. Again, this implementation is called a work list algorithm. You do an initial sweep to build up a set of elements that you need to do some work on, and then you kind of remove those elements one by one, and you keep going until the work list is empty and you're all done. So this is a work list algorithm. Work list is a set of nodes that still need identifying the shortest path through them. Right, so we're kind of working through the graph, kind of layer at a time. We're going to start by building up the work list and initializing data. This is, basically a convenient Python, our convenient hack for infinity, and this is our convenient hack for undefined node types. Add every vertex to the work list, and we're going to eventually go through all of them. We're going to produce a shortest path from the start node to every other node. And then we sort of seed this algorithm by assigning or just stipulating that it takes 0 cost to go to the source from the source. So that'll kind of be by stipulation. And then we work through the work list, and we find every vertex that has the smallest distance to it. So again, it's kind of like almost like a greedy algorithm where for all of the vertices that are currently left to consider in the work list, you pick the one for which the distance is the smallest, because that's the one that you'll want to go through essentially as much as possible. So in other words, if I start off at the source, well, the source currently has the lowest distance at the beginning. All of the other distances are infinity. And so I'm going to start at the source, and then I'm going to work my way through the graph from that source. And I'm going to keep track of which of those neighboring nodes from the source node have the lowest cost to get to. And eventually you'll kind of build up this profile where you say, well, I could use this one path, but if I go through this other path instead, I can get to the destination node faster. And that's kind of what this work list is getting at, where we're kind of considering all of these neighbors and trying to work through which of the nodes has the smallest distance, and then update the distance dictionary accordingly. All right. So let's see again. Will this work for a smaller, a more complicated section? Graph input. All right. So maybe I'll have a not so simple 3-dot graph where I'm going to go back to consult my awesome. We had a graph image thing that looked tempting. All right. So this one right here. Let me bring that down. All right, so if I want to specify this in inputs, technically this graph does not have directed edges, but that's okay. We will make up our own directions. We do what we want. All right, so I'm going to start off in A, and there's an edge from A to D with weight 1. There's an edge from A to B with weight 6. There is an edge from D to B with weight 2. There's an edge from D to E with weight 1. how would we want to do this? There is a, I guess it won't matter. We'll just say that it's a edge from B to E with weight 2. There's a B to C with weight 5, and there's an E to C with weight 5. Right, so we have captured all the edges in this magical graph here. Let's see, does Python have it, is Python happy with our implementation? It seems to be doing something. Let's confirm. First, before we do that, just again, as a matter of good practice, I'm just directly printing these things out. Maybe we don't want to do that. There's a couple things you can try. In Python, there is actually a package called pprint. So I will, for doing pretty printing. So I'm going to import pprint, and I'm just going to say I want to pretty print this dictionary, and I want to pretty print this other dictionary, and let's see what happens. No help, sadly. Too bad. Sometimes it works for like big JSON objects. What we'll do then is we will just iterate through all of the things. So we're going to say for every key value in distance dot items. So for every key value pair in the distance, we're going to say we're going to print out that the distance from K is value, right? And then for every key value pair in previous dot items, if you start at K, must go through V. I'll full screen this again. Oops. All right, so what we're saying is, again, with this previous dictionary, if I'm at node K and I want to go to the source with the shortest path, I must have come through this other value, value node. All right, so what does that look like? Let us take a look. Cool. All right, so a few things, and let's compare this against our intuition, which seems to match eerily perfectly with the table that is here. Sadly, I just noticed that. Hopefully, we will still be alive after this extremely long video. All right, the what we are saying, what we've computed is, if I want to go from node A to node B, the shortest path takes 3. And that matches our intuition, because if I want to go from A to B, I'm not going to take this one. That's too long. I'm instead going from A to D to B. That takes a total of weight 3. Now, similarly, again, if I start at A and I want to go to A, I'm already there. A to C, that's going to take 7. How is it doing that? Well, it has this red line is what's being taken. I go from A to D to E to C. No problem. D again, A to D, sure, and then A to E, I go from here to here. Great, right? So I seem to be computing correctly the shortest path between A and every other node in this graph. Now, this other part, interpreting what's going on here. This is, I don't like the phrasing that I've used here. So instead of starting, technically we're not starting there. It's like, if we reached K, we must have gone through V for the shortest path. that's kind of the interpretation here. So let's, all right. No, it's much too long here. All right. Cool. So if we reached C, we must have gone through node E, which is its immediate parent, through the shortest path. That makes sense. Again, if we're going to C, we went from A to D to E to C. So if I reached C, I must have come through E as part of the shortest path. What this will allow us to do is kind of work backwards to reconstruct the entire shortest path between each node. How does that look? So again, if I'm at C, I must have come through E. If I'm at E, if we reached E, I must have come through D. And if I have reached D, I must have gone through A. I must have started at A. Okay? So we can reconstruct that. Let's just do that quickly programmatically. Where I say, let's make another dictionary. We're going to report all of the shortest paths between the source node A and every other node in the graph. We're going to report the whole path taken. So that's going to be another empty dictionary. And what I'm going to say is, for every key value pair in previous, we'll say the paths of K we'll do it this way. So we want some sort of function, get path, where we're going to take in a node, like a vertex as input. And this is going to be a recursive function. And so we say, if we're going to have a vertex and then a path that we're going to form up. So if our vertex is the source, then we return nothing. Otherwise, we're going to return previous from the source and we're going to put that in a list plus get path prev source. So the source stays the same. Prev source and the path. I don't think we actually need that. So let's just keep that. And now just to check, I want to print out get path from A to C. Prev source is not defined. Yeah, and so, So we are going to rebuild this path. I want to say every time I come up with so if I come from A to C, A to C, A is not C. So what I want is the previous of previous of the vertex, previous of the vertex. Great. And that should be why don't we do it this way? So technically what I want to say is we're returning the vertex itself. Plus, okay, great. So this is a helper function to reconstruct path from source to given destination. And the base case is if we found the source, we're done, and return it. So that's the last step that we need in our graph. Otherwise, add the vertex to our path list and recursively call using the next entry in the prev dictionary. All right, so that's what that allows is this recursive formation of a new path. But again, probably other ways to do it. I think this will be acceptable. And then again, for good measure, just to report it for everyone, I want to say for every vertex in vertices, I'll say paths of that vertex is get path from, again, we'll start at A and we'll go to that vertex. And then at the ends, we will print out all of the paths. Let's see how that works. Again, all right, so for key value in paths.items, we will say print node, well, we'll say the starting vertex requires going through all of those vertices in that path, and we shall just say formats k equals k, v equals v. Amazing. All right, so like I said, matching our intuition before. If I want to go to C, I need to go C, D, A. You're right. So this is kind of matching what we can build up from this input graph. So we seem to be working. One last thing that we might want to do is to reverse these lists. Again, technically, if we're starting at node A, maybe it's more intuitive to read it from right to left. So we can also bring back our handy reverse code, where we'll just say, why don't we do like reversed of whatever is returned by that getPath helper function, which it turns out creates some type of iterator, which we can also fix by throwing it back into a list. Great. So again, going from C, we start at A, go to D, E, C. Perfect. This, again, just to clarify, reversed creates an iterator, which is a separate type of object that is meant for like memory efficiency and iteration over large objects. The thing is, it's not quite the same as a list, but you can force it to be one by throwing the iterator into a list, and it will go through all of the elements provided by the iterator, create a list out of it. Not always the most performant method, but again, for this homework, probably good enough. All right, so this has somehow taken an hour and a half. I hope that this was useful. You've kind of seen me the kind of go through this thought process of building up an algorithm, providing adequate documentation, thinking through how I can turn the algorithm that's described at a high level in Wikipedia into actual Python code using the tools at my disposal. Now, like I said, there are probably other ways to do some of these things, right? Like I just happen to know about the list constructor and the reversed iterator creator, but you can find all sorts of different ways of doing things, and there's no one single good way of doing this. This is kind of a key aspect of doing software design. So in addition to the compiler theory stuff that we will cover in the course, my hope is that this type of programming, this type of system programming where you're developing a set of tools in your toolbox as a developer and figuring out how you can put them together to make a big software system is a really critical goal, outcome that I want you to have in this course. And so this kind of puzzle solving approach to doing these homeworks is intended. Now, this is Dijkstra's algorithm for shortest path. Again, this is not quite what you would be doing. You're doing topological sort, but this can at least help you get started. Again, it's in the actual PA1 assignments, you don't need edge weights. It's just, you're given elements like 2 lines at a time that represents the edges between them in an eventual graph. And so there's a bit more algorithmically to do, but it can also be simplified a bit because we're not dealing with edge weights. So with that, I will end this video and hope that it adequately prepares you for getting started with PA1. As always, please feel free to reach out on the piazza if something is unclear. Thank you.